This video is on linear equations versus exponential equations. We're going to look at the difference between linear functions and exponential growth and exponential decay equations. We're going to look at the difference between what the equations look like, what the y values in the table looks like, the recursive equations, the shape of the graphs, and what the end behavior will look like, and how they differ from each other. So for linear, the equation looks like y equals mx plus b. This is when there is no exponent seen. There is an exponent on your variable x, but it's a 1. You just cannot see it. We have the letter x in here, but the exponent on the x is 1, so you cannot see it. For linear equations, the m is your slope, because it is your coefficient of your x, and your b is your y-intercept, because it is the constant of the equation. Exponential growth and decay have the same type of equation. Y equals a times b raised to the x is both of the equations, because it's exponential. The difference between exponential growth and decay is the value of your b. The difference between linear and exponential is that for exponential, the x is the exponent for both. The x is the exponent. That's how we know it's the exponential. Now before we had that the coefficient was your slope. The a value here looks to be like a coefficient, but it is still your constant value. The a value for both is your y-intercept, because this a value is not attached to the x, just like the b value in linear is not attached to the x through multiplication. The a value here is not connected to that exponent of x. Only the b value is. So for exponential, the b value tells you if it's growth or decay. This is called, since this one is growth, this is called our growth factor. This is the factor of which it will be growing. This value, for it to be growth, this b value is going to be greater than 1, not equal to, because 1 to any power will be 1, and that will not grow. So for exponential decay, the b will be called your decay factor. It's the rate at which it is decaying. Now for decay, your b value must be lower than 1, but it must still be greater than 0. It needs to be positive. It needs to be positive so it will actually decay or grow. It's got to be smaller than 1 so that it will get smaller, but it still needs to be positive. So the three different equations, or technically there's only two different equations, linear y equals mx plus b, and exponential is y equals a times b raised to the x power. Only the b is being raised to the x power. The difference between growth and decay is the value of the b. If the b is bigger than 1, then that value is going to be growing. If the b is smaller than 1 but still positive, it will be getting smaller, it'll be decaying. So if we look at a table of values, as the x's increase by 1, the y values in the table for linear will increase or decrease, depending on the slope, at a constant rate. That means that we're just going to add or subtract the same value. So we will be adding our slope or we'll be subtracting our slope depending on if it's an increase or decrease equation. For exponential growth, your y values in your table will be increasing but we'll be multiplying. So instead of adding or subtracting, all the y values will be multiplied by a number. So increase by multiplying. This could also be increase at an increasing rate. So when we increase by multiplying, our y values will be multiplied by a number larger than 1. So if we're talking about exponential decay, these values will be decreasing, but also by multiplying. And this would be, it will decrease at a decreasing rate. That's another way of putting this. So as we're decreasing by multiplying, we're going to be multiplying by a number smaller than 1, but still greater than 0. So we will not be multiplying by a negative value. We will be multiplying by a number smaller than 1, but still must be positive. You can also look at this as you are dividing by a number. So multiplying by 1/2 is the same as dividing by 2. The recursive equations, those are the now next, are going to look slightly different. We're going to use the true recursive equations using the a sub n and the a sub n minus 1. As a reminder, a sub n really represents the next value, and the a sub n minus 1 represents the now value. So for linear, we'll have the a sub n, so our next, is equal to our a sub n minus 1, which is our now, plus some value, whatever the slope is, and a sub 1 equals some number. You also might have it as a sub n equals a sub n minus 1 minus a specific value, because we are adding or subtracting, where a sub 1 is equal to a specific value. This is because we're adding or subtracting. Now with recursive, we would be multiplying by a specific number. So our next would be a sub n equals our a sub n minus 1, which is our now, times a specific number, which you could also rewrite this as a sub n equals a number times a sub n minus 1, where this number, as a reminder, must be bigger than 1 for it to be growth. So the recursive equation for exponential decay would look the same. This would be a sub n, so our next is equal to our now, a sub n minus 1, times a number, because we're decreasing it by multiplying. Again, we can have it as our number times a sub n minus 1 as well. This number must be a number that's smaller than 1, but it still must be greater than 0. So it must be positive, but it must be smaller than 1. So again, recursive goes with the next value is equal to your now. You're either adding or subtracting something for linear, or you're multiplying by your value in exponential. The shapes of the graph. Linear is a line. It has a slope. It has a constant rate of change. So this would have a positive slope. You could also have negative slopes, you could have undefined slopes, and you can also have 0 slopes. But linear is a line. The shape of an exponential is going to be a curve. Now, exponential growth will increase at an increasing rate. So that means that as it's going towards the x's are going positive, the graph is increasing, but then it starts going even faster. That's what increase at an increasing rate means. Now, it does kind of flatten out on the x-axis. It generally does not go below the x-axis unless you have a vertical shift. So we want to show that it's going to hug the x-axis, but it does increase and it gets faster and faster as it continues. Exponential decay will decrease at a decreasing rate. So it's actually going to start decreasing very quickly, and then it'll start slowing down as it gets towards the x-axis, and it'll start flattening out along the x-axis. But it does decrease, but it's starting to go slower as it gets towards the x-axis. So using the graphs, we can look at our end behavior. End behavior means as x's go left and right, what do the y's do? Linear, because it can have a positive slope or a negative slope, we're going to look at both. For a positive slope, as the x's can go to the right and to the left. So to the right means as x goes to positive infinity, meaning it's going to the right, and x's can also go to the left, which is negative infinity. So we have the right and the left. The y's will go to a specific value, and we're also going to look at for a negative slope. We're going to look at the same information. So as x goes to the right for positive infinity, and as x goes to the left for negative infinity, what do the y's do? So for a positive slope, if this is a positive slope, as the x's are going towards the right, the graph is going up. That means that the y values will go towards a positive infinity as the x's go to the right. Negative infinity states that as the x's go left, towards the left, the y values are actually going down forever. So that means that they're going to go towards negative infinity. So if we look at a negative slope, so I'm just going to draw a negative slope here. As the x's go towards the right, so as we keep moving towards the right, the y values are going down, so the y's would go to negative infinity. As the x's go left, so if I keep drawing this to the left, the y's are going to keep going up, so the y's will go to positive infinity. And we can sketch the graph to see what's happening to our end behavior. So if we look at exponential growth, as the x's go towards positive infinity, and as x's go towards negative infinity, the y's will go to a specific somewhere. So again, positive infinity, x goes to positive infinity means what direction is going to the right, and as x go to negative infinity, that's towards the left. As this graph goes towards the right, this graph is going to continue going up and up forever, so it'll go towards positive infinity. So this graph goes up forever. But as the graph goes towards the left, it's actually flattening out along the x-axis. It will not go below that x-axis. So our graph will actually go towards 0 because it flattens out. We're going to write that here. It flattens out but doesn't reach 0. This is called an asymptote. An asymptote. An asymptote is a value that is approached but never crossed. So we will approach that 0, so y is going towards 0, but it will never actually reach the value of 0. It'll keep getting smaller and smaller and smaller, but it will never actually reach the value of 0. So if we look at exponential decay, as x's go towards the right, and as x's go towards the left, what will the y's do? So as x approaches positive infinity, which is the right-hand side, as we go towards the right, the graph is flattening out again along the x-axis, which means that it is approaching the y value of 0, but it never actually crosses it. So it's flattening out at that value of 0. As x's go towards the left, which is the negative infinity. So as x approaches negative infinity, that means that's going to the left. The y values, as I keep moving left, are going to keep going up, so it'll go towards the positive infinity. The end behavior is asking, as the graph goes towards the right, what is happening with the y's? And as the graph goes to the left, what is happening to the y's?